pleasure and privilege to be with you this afternoon. This is to celebrate Ma'am Winnie's almost 45 years of invaluable service to the Department of Mathematics and Statistics, MSU-IIT Institute of Technology. Before anything else, I would like also to greet those who are tuning in via Facebook. Magandang hapon po sa inyong lahat. To start off, we have with us the dynamic Dean of the College of Science and Mathematics to give his opening remarks, Dr. Ephraim D. Metilio. Sir?
Thank you very much, Kathy. Can I be heard?
Yes. Yes, sir. Loud and clear.
Yes. The connection is a bit delayed, but yeah, I hope that my message will be heard clearly. Okay. So good afternoon, everyone. Welcome to this afternoon's very important occasion. Before proceeding, please allow me to acknowledge our Chancellor, Dr. Sukarno Tanggol, represented this time by our Vice Chancellor for Academic Affairs, Dr. Franco Teves. Also, MSU-IIT officials who are faculty members of CSM Department of Mathematics and Statistics. We have Vice Chancellor Dr. Gaudencio Pitalcorin Jr., Registrar Dr. Jocelyn Villela, CSM Assistant Dean Dr. Susan Dagundon, and of course our Department Chairperson Dr. Randy Cagaanan, all the Department Academic Program Coordinators, fellow workers in the government. And let me acknowledge also our invited guests and speakers. We have former CSM Dean, Dr. Severino Herbacio. Good afternoon po. Dr. Penilin Akal, Dr. Emiliano Maravilla, Dr. Sergio Canoy. And also we have our former CSM Dean and Vice Chancellor for Academic Affairs, Dr. Arnold Fusupe. We have our retired department professor, Dr. Chita Evardone, and the others I have missed. I apologize. And to all the guests and participants of the webinar, I was told that we have participants from other universities in Mindanao and in the country. But most importantly, our honoree, our retired but never tired, Dr. Rowena T. Isla, and also her family. I was also informed that Ma'am Weng's family is listening to us. And Dr. Randy Cagaanan informed me, when Dr. Randy informed me, I immediately accepted the job to give the opening remarks because Dr. Isla is a good friend of mine, being a sister of a very good friend of mine, former Dean of MSU-IIT Graduate School and retired Professor Dr. Alita Rojas. I'm a bit emotional, so I kept on clearing my throat, because Dr. Rowena Isla is one of the highly respected professors of CSM and in mathematics and statistics discipline of the country. She is a highly published professor and have rendered valuable service to MSU-IIT and our country in the field of mathematics. As Dean, it pains me to see our brilliant and persevering faculty members retiring. And I think this year there will be 4 more who will be retiring, and it feels really sad because I see them as pillars of the college, and supposedly we cannot afford to lose them in the college. In fact, in many universities in the United States and in other countries in Europe, very productive and tenured faculty members and professors and Nobel laureates can retire whenever they want, no? So they have the option when to retire because they are treated as a very valuable resource and treasures, having all the wisdom, knowledge, and experience in one's discipline. But we are in the Philippines, and there's always a turnover of professors in universities. Uh, well, Dr. Isla is retiring, but I'm pretty sure she has contributed a lot in training the next generation of mathematicians and statisticians in the country. I am sure she is retiring, but the department is very much stable and secure in maintaining the excellent standards of the discipline. Of course, Ma'am Wing Isla, we will always welcome you here in CSM with your future engagement with the department. So again, welcome everyone to the Graphs and Memories, a webinar in honor of Dr. Rowena T. Isla. Have a productive afternoon, everyone, and thank you.
Thank you, Dean Rectilio. Indeed, we are here today to give tribute to Professor Dr. Rowena T. Isla. I would like also to say good afternoon to the family members who are here with us today. I can see Dr. Rojas. So later we will see. Sino pa ba nito? Sorry, hindi ko na makita. Now, to get to know her better, let us watch the following video clip about Mom Winnie. Sir Rance. Graphs and Memories, a webinar in honor of Professor Dr. Rowena T. Isla, aptly conceptualized for our honoree for her almost 45 years of invaluable service in the Department of Mathematics and Statistics of MSU-IIT Institute of Technology. Dr. Rowena T. Isla was born on December 15, 1956 at Iligan City. She is the second of 8 children of Nena and Pedro Timonera Jr. Mom Winnie, as we fondly call her, in the department is happily married to Engineer Armando Isla Sr. They have 4 children, namely Dr. Armando Isla Jr., Zarina Isla Valladolid, Joanna, and Leandro. Mom Winnie has 2 grandchildren, Summer and Ziggy. She finished her elementary education at Iligan City South Central School in 1969, and she graduated as the Glass valedictorian on 1973 at Iligan City National High School. In 1977, she finished her BS Mathematics at UP Diliman, and in 1984, her Master's in Mathematics with a specialization in projective geometry at Ateneo de Manila University. In the year 2000, she finished her PhD in Mathematics with specialization in graph theory, combinatorics, and algebra here at MSU-IIT under the supervision of Dr. Severino V. Hervasio and Dr. Sergio R. Canay Jr. She joined MSU-IIT on June 20, 1977, wherein at that time the department chairman was Dr. Brigida Roscoe. She later served as the chairman of the Department of Mathematics and Statistics from July 1987 to April 1989, and was again the chair of the department on June 2007 to May 2008. She also served as a special assistant to the Office of the Vice Chancellor for Research and Extension from June 1989 to October 1990. She was the Mathematics Graduate Program Coordinator from June 2003 to October 2004. The DMS family has found a treasure in Mom Winnie. She's like a book filled with values and brilliant ideas. In our department, Mom Winnie is our go-to whenever we need guidance in our write-ups, whenever we need a coach for the essay writing and oratorical contest. She is our go-to for sound opinions and advice on any project or activity of the department. Her wisdom, calmness, kindness, and sweet, gentle smile light up the math department. She teaches math like a breeze. Yun bang, mahirap yung proof, tapos mahaba pa, tapos di mo namalayan, tapos na niyang i-prove. That's Mom Winnie, definitely a woman of talent and brains. Her professional experience include being an instructor, assistant professor, associate professor, and now a professor of the Department of Mathematics and Statistics of CSM. She had supervised several undergraduate theses, master theses, and doctoral dissertations. She also had reviewed papers in some journals in mathematics. Dr. Rowena T. Isla is also a recipient of the following awards: Outstanding Faculty in Mathematics and Statistics for Web of Science, ISI or Scopus Research Publications. Outstanding Faculty in Mathematics and Statistics for paper presentation in an international conference. Natatanging mananaliksik sa larangan ng Sipnayan, awarded by MSU-IIT last February 2019. Ruby Award, 40 Years Service Award. Gawad Chancellor sa mga natatanging mananaliksik sa larangan ng Sipnayan at Estadistika. She was granted a 1-year sabbatical leave by MSU-IIT last 2015. Dr. Rowena T. Isla also had several publications, research papers published. To mention a few, we have K-Fair domination in the joint corona composition and Cartesian products of graphs, co-authored with Isi Marivilla and S. Arcano Jr. Along with this is the fair domination in the joint corona and composition of graphs, both published on Applied Mathematical Sciences. Also, fair total domination in the joint corona and composition of graphs, still co-authored with Isi Marivilla and S. Arcano Jr., which was published in the International Journal of Mathematical Analysis. And the list goes on and on. Mom Winnie is undeniably one of the pillars of the Department of Mathematics and Statistics. Her accomplishments and achievements worthy to be emulated. Mom Winnie had served the department with high ideals and dedication. She is one of the reasons why our department is a center of excellence in mathematics. We cannot thank Ma'am Winnie enough, but we hope that this webinar in her honor is a testimony of our gratefulness and a reminder that we treasure her and her contributions to the DMS family, her family. Finally, please allow me to recite a poem which was written last November 3, 2021. The day I learned of Mom Winnie's plan to retire. Reading between the lines, more so with mathematical facts. If winning is the game,
Now even words can play. The unknowns, A's and B's. Abstract it may be for some of us to see. For its truth to come true, read again and search. Fallacies may appear, but they're actually not there. Can fractal equation be an answer? 11 be a clue. Written last November 3, 2021. For Mom Winnie, whose simplicity, beauty, talent, intelligence, and values truly inspire. Graphs and memories.
That poem is actually an acoustic poem, Ma'am Winnie. At this point, to represent our Chancellor, let us hear a message from our Vice Chancellor for Academic Affairs, Dr. Franco G. Teves. Sir?
Yes, greetings to all, especially to our honoree, Dr. Rowena Timonera Isla. Yeah, well, I was really surprised. I didn't realize that Wendy is already retiring. When I got the invitation this morning from Randy, Dr. Kagaanan, really, I was a little bit surprised, okay, because I thought that Wendy is still retiring, not in the very near, not this year. But first of all, let me greet some of the guests who are here with us. I'm glad to see Dr. Hervasio is here, and Dr. Supe was mentioned also, and all the colleagues and friends, especially at the Department of Mathematics and Statistics. Well, I'm supposed to represent the Chancellor, and I'm glad that I'll be representing him, but I'm also happy to be here because actually Wenny is a very special person. No? Not only is a colleague, but I don't know if Wenny knows it, but we are actually related. The Iliganons are related. I think which branch? The Ramos, Ramiro, Halibas, Gaite branch. And your Lola Bebang we also call her Lola Bebang. Okay, so Alit, the master, is here with us. Your sister is also a very close friend, and she knows more about this. Anyway, it's really a privilege to be here. This is a very special webinar, and because you will also be celebrating your probably I don't know, but I hope this will not be your last lecture when in IIT. I hope that there will be many more lectures that you are going to give in IIT. Now, yeah, just like you, many of us have grown professionally in IIT. We have grown here. We have developed professionally while working in MSU-IIT. And because we are so engrossed with our teaching, we sometimes forget that time is catching up with us. And for all we know, we are already retiring. We're so busy working, teaching, all of this, all of that. And then suddenly we realize that we are about to retire. And I will be joining you next year, actually. I'll be joining you next year. Well, anyway, I would like to take our life as, episodes of chapters, and post-retirement is just another chapter. And what's life after retirement? That will be another chapter to be written. And I'm very sure that you have a lot of things to write when during your retirement life. But I'm really sure that you will still be very busy. Okay. And I really am praying that you'll still continue to be fruitful, sharing continually your expertise to others. And I really am very sure of that. You're going to continue with that even after you retire. So what can I say but all the best for you. God bless you. And may you have more successes and more fruits to come even during retirement. Thank you very much and good afternoon.
Thank you, Dr. Teves, for your message. But before you go, sir, we would like to request for a commemorative photo with you, with Dean Metilio and with Dr. Isla. May we request somebody, Sir Rands, for the photo op?
Yes, ma'am. Yes, ma'am.
Thank you.
You can already.
Okay na po. Thank you. We are now ready to proceed to the series of talks. We would like to remind everyone that after each talk, you're encouraged to type in your questions and your comments at the Zoom chat box. But should you prefer to speak up and directly ask your questions to the speaker, you may use the raise hand feature at Zoom and wait to be acknowledged by the moderator before unmuting yourself. I hope that this instruction is clear for everyone. Let me start as the first moderator. Our first speaker is a great influencer in graph theory. He's one of the best and prolific writers in this field. Dr. Severino Hervasio, now a professor emeritus of the Department of Mathematics, College of Science of the LaSalle University, was the former Vice Chancellor of Research and Extension of MSU-IIT, former Dean and Faculty of the Graduate School of CSM. His academic background includes being a graduate of Mapua Institute of Technology for BS Mechanical Engineering, University of the Philippines for his Master's in Math, and Ateneo de Manila University for his PhD Math. He is also a registered mechanical engineer. He had served various institutions. To mention a few, UP at Los Baños, UP Diliman, Ateneo de Manila University, DLSU Manila, Mapua Institute of Technology, and of course, MSU-IIT Institute of Technology. He had conducted seminars and trainings as a seminar director and resource person on number theory and graph theory research groups, as well as thesis advising seminars. He is a recipient of various awards and distinctions. To name a few, he was a UP NSDB Graduate Scholar from 1966 to 1968, UP Faculty Fellow from 1974 to 1977, Research Fellow on July to August 1976, Exchange Scientist to Japan on March to June 1986, and on month of October of 1989 and 1992. In 1981, he was declared one of the 10 outstanding scientists in the Philippines. In 1992, he was given an Achievement Award by the National Research Council of the Philippines. He was given an Outstanding Teacher Award not only once, but twice, one in 1997 and another in 2006. He received a research award in 1999. Then in 2009, after his commencement speech at Mapua Institute of Technology, he was awarded as an outstanding Mapua alumnus. He had written and co-authored almost 100 published research papers. Dr. Severina Hervasio, aside from being a prolific writer, has mentored numerous undergraduate and graduate students, and one of them is our honoree, Dr. Rowena T. Isla, and Dr. Hervasio, along with Dr. Canoy, also one of our speakers, were the dissertation advisors of Dr. Isla. Ladies and gentlemen, to give his talk on edge intersection graphs, path, triangle, square, and pentagon graphs, let us give a virtual applause to Dr. Severino V. Hervasio. Sir, the virtual floor is now yours.
Thank you very much for the kind introduction. When I received the invitation to give a talk in this occasion, without hesitation, I accepted because this is a great opportunity for me to express my gratitude to Dr. Isla, or Winnie as we call her, especially for serving as a special assistant in my office when I serve as Vice Chancellor for Research and Extension. The title of my talk is Edge Intersection Graphs, specifically path, triangle, square, and pentagon graphs. This actually still an ongoing research. In fact, I started doing this with some of my colleagues just last January, and we have not gotten much results, but I think it's good enough for presentation. So for the outline of my talk, I'll give an introduction, then talk on path graphs, triangle graphs, square graphs, pentagon graphs, and I will show you some of my references. So here is a formal definition. Let G be a given graph and let H be any other graph. We denote by script E sub H of G, the graph whose vertices are the induced subgraphs of G isomorphic to H. So we collect all the induced subgraphs of G isomorphic to H. They will become vertices of our new graph. And two vertices will be adjacent if and only if the associated induced subgraphs share a common edge, at least one common edge. The graph E sub H of G is called the edge intersection graph of the induced subgraphs H. Induced subgraphs isomorphic to H. We look at E sub H as a graph operator. So it applies to a graph, which can be applied iteratively. If G does not contain any induced subgraph isomorphic to H, we set E sub H of G to be the empty set. Actually, strictly speaking, no graph has an empty vertex set, but for convenience, we'll denote by the empty set the result of applying the operator E sub H to the graph G in case G contains no subgraphs, no induced subgraphs isomorphic to H. For any integer k greater than 1, we define e to the k, so k iterated intersection graph, e to the k of sub h of G to be e sub h applied to e to the k minus 1 sub h of G. Now, in succeeding discussion, I will replace H by specific subgraphs like paths of order 3. We can make these triangles or C3 or K3. H can be C4, induced C4 or square, and H will be made later on pentagon, an induced cycle of length 5. So instead of defining repeatedly the edge intersection graph for each of these, just combine them into one. For any subgraph H, for any induced subgraph H, we define the edge intersection graph. As a very simple example, let G be the path P sub 5, shown here below. so a path of order 5, and let H be P sub 4, path of order 4. The graph G has exactly two subgraphs, induced subgraphs isomorphic to P sub 4, namely, as you can see, 1, 2, 3, 4. That is an induced path. So it is isomorphic to P sub 4. And another one is 2, 3, 4, 5, exactly two of them. And those two paths, two induced paths, P sub 4, share actually two edges in common, 2, 3, and 3, 4. The requirement is at least one. So the vertices of our edge intersection graph will be the induced subgraphs isomorphic to P sub 4, namely I denote them by this 1, 2, 3, 4. So that's the path 1, 2, 3, 4. And the other one is 2, 3, 4, 5. They are adjacent in the edge intersection graph because they share at least one common edge. So the edge intersection graph of P sub 5 with respect to H, which is equal to P sub 4, is isomorphic to P sub 2. Okay. Let G and H be graphs and consider the sequence e to the k sub h of G from k equals 0 to infinity. When k equals 0, we regard this to be the graph itself. So the first element of our sequence is G, followed by the first iterated edge intersection graph, P sub h of G. Then apply E sub h again to this, you get E square of sub h of G, and so on. Either of the following three things can happen. There are three possibilities. Number one, there exists an integer k greater than 0 such that e to the k sub h of G is the empty set, meaning there are no vertices. So the previous graph before this one contains no induced subgraphs isomorphic to H. So the next iteration will give us the null set. That is one possibility, it can happen. Second possibility, the sequence contains repeated graphs up to isomorphism. Okay. Up to isomorphism, repeated graphs up to isomorphism. And third possibility is the sequence does not contain isomorphic graphs. And based on these possibilities, we classify graphs into three groups or classes. Here is the definition. A graph G is called H vanishing if it satisfies 1. So if there is a positive integer k such that the k iterated edge intersection graph is the null set. That is H vanishing. G is called H periodic if it satisfies 2. Maybe at this point it is not clear why the term periodic was used, but it will be explained later. So that is the case when the sequence contains repeated graphs up to isomorphism. And thirdly, we call it H expanding if it satisfies condition 3. That is the sequence of the k iterated edge intersection graphs does not contain isomorphic graphs. This is now the justification for the choice of terms. If for some integer k greater than 0, E sub h, there should be a superscript k here, I forgot. E sub h to the k of G is the null set. Then eventually the graph G no longer contains induced subgraphs isomorphic to H. In other words, H eventually vanishes. And that is the reason for using the term H vanishing. For periodic, the sequence of k iterated intersection graphs contain isomorphic elements. So isomorphic graphs are here. Let us assume that E sub h to the m of G is the first element in this sequence that is repeated up to isomorphism. And so there is a smallest integer p greater than 0 such that if you apply E sub h to this p times, so E sub h to the m plus p of G is isomorphic again to E sub h to the m of G. The first time, this is the first graph repeated, E to the m sub h of G, and it occurs as early as after P more iterations. Then, if we apply E sub S to the T to both sides, E to the M plus P plus T of G is isomorphic to E to the M plus T of G. And if we put N equals M plus T here, combine M and T together, then E sub H to the N plus P of G is isomorphic to E sub H to the N of G for all integers N greater than or equal to M. And P is called the period of G. So that is the justification for using the term H periodic. And the period is this P. Then for the last, it must be obvious, if all the elements of the sequence are non-isomorphic, it is clear that the limit of the cardinality of the vertex set of E to the K sub H of G is infinity, goes without bound. Okay, and that is the reason for using the term H expanding. So the study is all about edge intersection graphs for some special induced subgraphs H. As mentioned in the title, we will take H to be a path of length 2 or a triangle or C3 or K3. We will take this to be an induced C4, so square. And lastly is H is a pentagon, an induced cycle of length 5. For path graphs, first topic. This, as I have said, is a study recently started as a joint work with Dr. Isagani Hos of the LSU. And some of our initial results will be presented here. I will avoid proving perhaps. So, but maybe some things that are easy to prove can be proven. We define the P sub 3 graph or path graph, okay, graph G, to be the edge intersection graph of the induced paths of length 2. An induced path of length 2 is P3, the order is 3, the length is equal to 2. So in our previous slide, the preceding slide, if H is taken to be P sub 3, we have the concept of path graph or P3 graph, the graph G. Here is an example. I have here a path. I forgot the label 5 here. So my graph G is P sub 5. My H is P sub 3. So 1 P sub 3 here is 1, 2, 3. That is an induced path of length 2. It becomes a vertex in the edge intersection graph. Another path of length 2 is 2, 3, 4. There. They are adjacent because the two paths share the common edge 2, 3. And lastly, we have also the path of length 2, 3, 4, 5. Here, forgot the label, 3, 4, 5, which is adjacent to 2, 3, 4 because they share the common edge 3, 4. So the edge intersection graph or P3 graph of P sub 5 is isomorphic to P sub 3. And in general, it can be shown that the edge intersection graph of P sub n greater than or equal to 3 is P sub n minus 2. I mean, isomorphic to P sub n minus 2. Another example is this. If my graph is the cycle of length 4, 1, 2, 3, 4, the paths of length 2 are 1, 2, 3. Here it becomes a vertex. Another path of length 2 is 2, 3, 4. There, they are adjacent because they share the edge 2, 3. Then 3, 4, 1, adjacent to 2, 3, 4 because they share the common edge 3, 4. And lastly, 4, 1, 2, adjacent to 3, 4, 1. Common edge is 4, 1. It is also adjacent to 1, 2, 3 because they share the common edge 1, 2. So this is interesting. The path graph of C4 is also C4. And in general, the path graph of a cycle, C sub n, provided n is greater than or equal to 4. It doesn't apply to C3, okay? Because C3 has no paths, induced paths of length 2. So for n greater than or equal to 4, the path graph of C sub n is isomorphic to C sub n. That's one observation. Here I put those results in a theorem. So I have mentioned already, if n is at least 3, the path graph of P sub n is isomorphic to P sub n minus 2. And if n is at least 4, path graph of C sub n is isomorphic to C sub n. Some remarks. Paths P sub n for n greater than or equal to 3 are path vanishing graphs. So that should be obvious from the example, because the path graph of P sub n becomes P sub n minus 2. It is slower in order by 2. So if you keep on applying the operator P sub 3, I'm now using P sub 3 instead of script E in the general discussion. If you apply the operator P sub 3 repeatedly, no matter how long this path is, eventually there will be no paths of length 2 and you get the null graph. So all paths are vanishing graphs. On the other hand, cycles are path periodic, provided the length is at least 4. Cycle periodic with period 1. Because we have seen from this P sub 3 of Cn is isomorphic to C sub n. So we have already examples of path vanishing graphs and path periodic graphs. Here is one more definition. A graph H is called a path graph. Path graph. If there is a graph G such that P sub 3 of G is isomorphic to H. In other words, a path graph is the result of applying the operator P sub 3 on a graph. And here we have a theorem. The complete graph K sub n is a path graph if and only if n equals 1, 2, and 3. This is almost trivial. I will not show the proof. So larger complete graphs are not path graphs. For example, K sub 4. K sub 4 cannot be obtained as the path graph of any graph. Only K1, K2, and K3 are path graphs. The graph I, denoted by P sub 4 bar P sub 4. This means two paths with a common edge. And the edge common to the two paths is their middle edges. This kind of graph, or this graph, is path periodic. Here is the graph I, P sub 4 and P sub 4. ABED, if you look at this drawing, it is a P sub 4. And CBEF is another P sub 4. They share the common edge BE. And I denote that graph by P sub 4 bar P sub 4. And this graph is path periodic. You try to compute or determine the path graph of I, it will turn out to be this. Look, the paths, induced paths of length 2 are, one is ABC, that's of length 2. We have ABE, there ABE, FEB, FEB, DEF, CBE, and DEB. It can be checked that these are the corresponding edges. You have here a complete graph at the center and two C3s here. Later on, we will denote this by C3 bar K4 bar C3 for convenience. And if you compute again for the path graph of this, it will turn out to be a cycle, C8. Okay. And therefore, application of P sub 3 to this will give you C8, no matter how many times you apply P sub 3, because that is a cycle of length at least 4. Therefore, I is path periodic with period 1. It's not only the cycles that are path periodic, but also this one, which in fact has no cycle at all. Another theorem, the graphs K23 minus E, C3 bar C4, and C3 bar sub E, C sub 4 bar is E prime C3, where E and E prime are independent edges of C4. So we are combining in the first here. This is K23, that's the complete bipartite graph. You delete any edge, no matter what edge you delete, it is you get something isomorphic, like this one. This is actually K23 minus E. It's K23 minus E. We claim that this is path expanding. This is if you take the path graph of this, it will turn out to be like this one. Let's not check the details. So that's the result. And this graph has this induced subgraph C3 bar C4. This one, this square. Maybe you can take this triangle. That is an induced subgraph. Now the path graph of this C3 bar C4 is this one. It is C3 isomorphic to C3 bar C4 bar C3. So to prove that all these three graphs are cycle path expanding, it is enough to prove that this one, the last one, is path expanding. Okay. Now, direct computation of induced paths of length 2 and adjacencies will give us this result. You apply P sub 3k times to C3 bar C4 bar C3, you will get K sub 2 to the K plus 2 bar C4 bar K sub 2 to the K plus 2. The graph looks like this. You have a C4 there at the center and two complete graphs here. And as K approaches infinity, of course, the order of this graph approaches infinity. So the graph will be under the classification of path expanding. So at least we have given examples of path vanishing, path periodic, and path expanding graphs. Our aim really is to give characterizations, but we are, I think, very far from that, still far from that. Here is another theorem. Let H be a subgraph of G such that all induced paths of length 2 in H are also induced paths in G. Then P sub 3 of H is an induced subgraph of P sub 3 of G. This theorem is quite useful, no? Also, we have shown this. The graph K sub 2, 3 minus E is the smallest path expanding graph. Here is an easy result. The planar grid P sub 2 box product P sub 3. Well, some people denote this by cross, no? But I guess this is becoming more popular. Box product P sub 2 box product P sub 3 is path expanding. And the proof is quite simple. This is P sub 2 box product P sub 3. And you can easily find this subgraph, induced subgraph, which is isomorphic to K23 minus E. But this is path expanding, and applying the theorem above follows that the planar grid P sub 2 box product P sub 3 is path expanding. And as a consequence, all planar grids PM box product P sub N that contains P2 box product P3 as subgraphs are path expanding. Another theorem, all cylinders CM box product P sub N, provided M is at least 3, N is at least 2, are path expanding. Here is an illustration. This is when M is equal to 3 and my N is just equal to 2. You can find here a subgraph isomorphic to C3 bar C4, which we have found to be path expanding. Therefore, the cylinder is path expanding. When M is 4 or greater, you can find a subgraph like this, isomorphic to K23 minus E. And we know that that is path expanding. So all cylinders, and with these restrictions, are path expanding. Another result, all toruses CM box product CN are path expanding. Now, K23 minus E is an induced subgraph of a torus if M is greater than T or N is greater than T. Here is an illustration. This is a torus. You can find this subgraph isomorphic to K23 minus E. So that's a square with a pendant edge there. And that induced subgraph is path expanding. So the graph of the torus is path expanding, provided M is greater than 3, N is greater than, or N is greater than 3. If N and M are both equal to 3, then C3 bar C4 is an induced subgraph of the torus. But I could not find an image of the torus where M and N are equal to 3. So anyway, it is easy to check. That is it. Let's go now to triangle graphs. I started this study very recently also with Dr. Rebet Lim of the LSU, and some of our initial results will be presented. The triangle graph of a graph G, denoted by T of G, is the graph whose vertices are the triangles or cycles of length 3. Definitely that is induced. Where two vertices, which are triangles, are adjacent if, wrong spelling here, sorry, typographical error, if and only if they share a common edge. For instance, the triangle graph of the wheel, W sub N, provided N is at least 4. This one is W5. 5 vertices outside. The triangle graph is isomorphic to C5 because there are exactly 5 triangles here. 1, 2, 3, 4, and 5 denoted by these symbols, 1, 2, 3, 4, 5. Of course, we don't count the bigger cycle like this one, C5, only the triangles. 1 and 2 are adjacent, they share a common edge, 2 and 3 adjacent, etc. So you form a cycle C5 here. And for the triangle graph of the wheel W sub n is isomorphic to C sub n. This one has no more triangles. So the triangle graph of this is the null set or null graph. It's therefore triangle vanishing. So the wheels Wn n greater than equal to 4 are triangle vanishing graphs. And it's not difficult to see that the square of a path is a triangle vanishing graph. If we just deal with the path, there are no triangles, but if we square a path, the black line, the black edges here are the edges of the path. And by adding the red edges, you get the square of the path. So now there are triangles, and consecutive triangles are adjacent. So the triangle graph of P sub n squared can easily be shown to be isomorphic to P sub n minus 2. Isomorphic to P sub n minus 2, a smaller graph, which has no triangles. So this is also a triangle vanishing graph. Next example. This is one of the Platonic solids, the octahedron. This is a solid with 8 faces, which are equilateral triangles congruent to each other. Octa, because it has 8 faces, 8 triangular faces. So there are exactly 8 triangles here in the graph. If you look at the 4 triangles above the square here, consecutive triangles are adjacent, so they will form a square in the triangle graph. This is square. And the 4 triangles below this square will also form a square at the bottom of this. And opposite triangles here share a common edge, so they will be adjacent, forming these vertical sides of the square. So the triangle graph of the octahedron is the hexahedron, which is commonly known as the cube. There are no triangles here, and therefore it is triangle vanishing. Another example is the icosahedron, this one. As you can see, there are 5 triangles here on top of this pentagon, and then 5 triangles below this pentagon, 10, plus down here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, I think 20. Yeah, 20 triangles. You form the triangle graph, it is going to be isomorphic to the graph of the dodecahedron shown here. The dodecahedron has 12. Only 12 here, no? 5, 5, sorry. Am I correct? 1, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 10, 11, 12. Yeah. And by the way, the triangle graph of the icosahedron coincides with the concept of Whitney dual. This, the graph of this is a planar graph, and the Whitney dual is the graph whose vertices are the regions of the planar graph, and 2 regions are adjacent in the dual. I'm sorry, in the Whitney dual, even only if they share a common boundary. So what we are going to get is the dodecahedron. The dodecahedron has no more triangles, so the icosahedron is also a triangle vanishing graph. Tetrahedron, my last example. This is again one of the 5 Platonic solids. There are 4 triangles here, and any 2 triangles share a common edge. So the graph will be isomorphic to itself. And hence we conclude that the tetrahedron is a triangle periodic graph. So we have seen triangle vanishing graphs and triangle periodic graphs. Now let's give a graph consisting of a complete graph K4 and where each edge has at most one hat. I will define a hat. A hat is this. U is a hat of the edge 1, 3. So a hat is a vertex adjacent to the end vertices of an edge. That is called a hat of the edge 1, 3. And V is a hat of the edge 0, 2. So let G be a graph consisting of a complete graph K4. So my K4 is this, whose vertices are labeled 0, 1, 2, and 3. And where each edge has at most one hat. So here, there are two edges with one hat, and some edges do not have any hat at all. You can put a maximum of 6 hats because K4 has 6 edges. It is known, so this is a known result actually, that such a graph is triangle periodic. The triangle graph of this will be equal to this graph, and it is isomorphic to the original graph G. So this is a triangle periodic graph. And in fact, these are the only triangle periodic graphs. Now, if a graph G can be expressed as the union of two graphs M and N, such that the intersection of M and N is just an edge of G, then we shall write, I have used this notation previously, sorry for that, M bar sub E N, or simply M bar N. The graph K4 bar K4 is triangle expanding. Here is K4 bar K4, two K4s, where there is an edge shade between the two, can be verified. So here, the vertices of the triangle graph are the triangles here, like 1, 2, 4 is a triangle here, 1, 2, 4, the red label. So that vertex represents the triangle 1, 2, 4. And we also have 1, 4, 5 here, 1, 4, 5 here, and they are adjacent to each other. I will not give all the details, but it can be verified. To compute for the triangle graph of K4 bar K4, it's going to be this. So it is K4 by K bar K4 bar K4. And it's easy to make a projection. No? You take the triangle graph of this again, inserted to this will be another K4, and inserted in this edge is another K4. It will become a longer series. So K4 bar K4 is triangle expanding. The graph K4 bar K4 minus E, where E is not incident to the edge common to the two K4s, is a triangle expanding graph. So this is the drawing. K4 by K4 minus E, minus this edge. That edge deleted is not incident with the common edge between the two K4s. This is a triangle expanding graph. It can be verified that the triangle graph of this is K4 by bar K4. But we have seen earlier that the triangle graph of this is K4 bar K4 bar K4. It is expanding. So this one itself is triangle expanding. And we conjecture, we have not yet proven this, but we believe the graph K4 by K4 minus E, this graph, is the smallest triangle expanding graph. Next, square graphs. I started this study with Dr. Dept of the LSU also. The square graph of a graph denoted by S of G is the graph whose vertices are the induced cycles isomorphic to C4, and where two vertices in S of G are adjacent if and only if the associated induced cycles share at least one common edge. If S of G is isomorphic to H, we call H a square graph. Here is an example. The graph G contains, you can see, 4 induced cycles of length 4, and they share an edge, this one. Therefore, the square graph of this will have 4 vertices, 1, 2, 3, 4, mutually adjacent, because any two squares share a common edge. Okay, and there is no induced square in this graph. No induced square. There are cycles of length 4, but they are not induced. Therefore, this is a square vanishing graph. The graph G, I mean. Example, the cube, the hexahedron. There are exactly 4, 5, 6 squares. They will be our vertices in the square graph. This 6, 1, 2 opposite each other, and then 4 here. It can be checked that the square graph of this is the octahedron. You might think that there are no squares here. No, there are induced squares here. For example, this is square, you can see that is induced. This one also, an induced square. In fact, there are exactly 3 induced C4s, but unfortunately, no 2 of them share a common edge. Therefore, the square graph of the octahedron consists of just 3 vertices corresponding to the 3 squares. And another iteration gives us the null graph. So the S cube of the cube is already empty. It is therefore square vanishing. The planar grid, by picture, I think it's easy to convince oneself that it is square vanishing. Here is an example of a planar grid. I mark the squares by red circles. So they are the vertices in the square graph, and adjacencies are shown by the red lines. So the red graph is also a planar grid, but it's smaller. It's isomorphic to P sub m minus 1, box product P sub n minus 1. So you apply it iteratively, you eventually get a graph without any square. So the planar grid is it's a square vanishing graph. Okay, the cylinder CM, box product P sub n, m not equal to 4, is square vanishing. In this illustration, you can find 4 squares like this in the graph of the cylinder that will form a square in this square graph. And this will go around to generate a cycle. But the height of the cylinder is 2. The height of the resulting cylinder after application of the S operator will be of height 1 only. So it is isomorphic to C sub m, box product P sub n minus 1. And eventually, to keep on applying this operator, squares will vanish. So the cylinder CM, box product Pn, is also a square vanishing graph. Now, here's the theorem. The torus C sub m, box product C sub n, m and n not equal to 4, is a square periodic graph with period 1. That is, square graph of Cm, box product Cn, is isomorphic to Cm, box Cn. That's easy to see here. No? Look at this torus. These circles represent these squares, and those 4 squares produce this subgraph, a square, and it goes round the torus. And it's easy to visualize and figure out that the square graph of the torus is isomorphic to itself. So far, the only square periodic graphs we have found are the toruses. We don't know of any other graphs. So that really shows this research is very new. No? We have spent barely 1 month doing this. So I'm sharing to you the results we have obtained so far. Lastly, the pentagon graph, a study I started with Ms. P.V. Ramos. I supervised her MS thesis during her graduate studies at UP Baguio. And some of the results we obtained so far will be given here. So the formal definition, the C5 graph, C5 of G, is the graph whose vertex set is the set of all induced cycles of length 5, or the pentagons in G. And 2 vertices are adjacent if and only if the associated cycles share at least 1 common edge. One theorem, all complete graphs are pentagon graphs. That's easy to figure out. I will not give the result anymore. The star graph, K sub 1n, is a pentagon graph even only if n equals 1, 2, 3, 4, 5. Also, I don't think this result is difficult, so I will skip the proof. The wheel W sub n is a pentagon graph even only if n equals 3, 4, and 5. Also, that's not difficult to verify. And the following are pentagon graphs. 1, the planar grids, Pm, box product Pn. cylinders CM box PN, M not equal to 5, and the toruses CM box CN, M and N not equal to 5, M even or N even. To illustrate, number one, planar grids. This is P4 box P8. Start with P4 box P8. There are no pentagons actually, but if we insert vertices like this, the red vertices inserted, we obtain a graph. So this is a modified P4 box P8 obtained by inserting some vertices. So now we have pentagons. This is a pentagon, this is a pentagon. So the number of pentagons is actually equal to the number of squares in the original grid. And when you form the pentagon graph of this modified P4 box P8, you're going to get a graph isomorphic to P3 box P7. So this reduced by 1, this reduced by 1. And by inserting vertices in properly selected edges, we obtain a graph whose pentagon graph is the given planar grid for any planar grid. Okay. Cylinders. We have a cylinder like this, for instance. We can insert vertices somewhere, like the red vertices inserted here, that will make all these squares in this cylinder pentagons. They are now all pentagons. And if you compute for the pentagon graph of CM box P sub n plus 1, it's going to be isomorphic to CM box Pn. So all cylinders are pentagon graphs. Proof of 3, toruses. A similar modification is possible in the case of a torus because of the restrictions M and N not equal to 5, M even or N even. Pentagon periodic graphs. We have found one pentagon periodic graph. The graph of the dodecahedron. Okay, there are exactly 12 pentagons here. They become the vertices of the pentagon graph. As a planar graph, the regions are triangles, but if you look at it as a general graph, there are in the graph of the icosahedron, there are cycles of length 5 induced like A, B, C, D, E, A. That's an induced cycle. And so we tried to compute or determine the pentagon graph of the dodecahedron, and the result was surprising. Here is an illustration. This is my dodecahedron. I label this vertex A, below it is B, and the rest 1, 2, 3, 4, 5, forming a pentagon here, and 6, 7, 8, 9, 10, another pentagon here. In the pentagon graph of this graph, we look at the pentagons. Take note that for every vertex like A has 5 neighbors, and those neighbors form a pentagon, which is induced. That's true for any vertex, like the vertex 1. The vertex 1 has neighbors A, 2, 7, 6, and 5, forming another induced pentagon. And so for convenience, in constructing the pentagon graph of the icosahedron, I labeled A the vertex corresponding to the pentagon 1, 2, 3, 4, 5. So here, 1, 2, 3, 4, 5. I labeled that vertex A. And the vertex B here is used as label for this one, corresponding to the pentagon 6, 7, 8, 9, 10, and so on. This one, for instance, the vertex 1 here determines the pentagon A5, 6, 7, 2A. A5, 6, 7, 2A, and so on. And it turned out that the graph, the pentagon graph of this is isomorphic to itself. That can be checked easily if you look at the labels. For example, these two vertices are adjacent because what pentagons do they represent? This one is 1, 2, 3, 4, 5. This is 2, 3, 9, B7, 2. And 2, 3 is a common edge of those pentagons. These two, for example, 8 and 6. This is for the pentagon 2, 3, 9, B7, and this is for the pentagon 1, 7, B, 10, 5. So you have here the edge B7. You also have your B7. So they are adjacent in the pentagon graph. So we are quite surprised by this result. The pentagon graph of the icosahedron is isomorphic to itself. And that makes the icosahedron a pentagon periodic graph with period 1. Or actually, the dodecahedron is pentagon periodic with period 1. If you start with the dodecahedron, you will get the icosahedron. Another iteration will give you the icosahedron again. Okay, I'm almost done. Let D and I denote the graphs of the dodecahedron and icosahedron respectively. The previous slide proved that the dodecahedron is a pentagon periodic graph since C to the n, C sub 5 to the n of D is isomorphic to I for all integers n greater than or equal to 2. So as I've said, it came as a surprise to us. We were not expecting that result. Now, after the first graph we tried was the Peterson graph, denoted by P sub 5, 2. The Peterson graph has pentagons also, induced pentagons. It turned out that the pentagon graph of the Peterson graph is the complete five-partite graph, K sub 2, 2, 2, 2, 2, which is free of induced cycles of length 5. So the Peterson graph is pentagon vanishing. And one question we have not answered is this: are there pentagon expanding graphs? I hope we can find the answer to this. Also, for square graphs, we don't know. We just found square periodic graphs, but we have not found any square expanding graphs. That is all I want. The references, by the way, these are old references. Sorry for that. Triangle graphs by Balak Krishnan, 1999. A paper of Egawa and Ramos, Dr. Ramos, a former colleague of mine in UP Los Baños, was, because he passed away, I think, about 6 years ago. He also wrote Triangle Graphs, 1991, with Yoshimi Egawa. And this is a related paper of mine, Cycle Graphs, published in 1984. Pullman, Click Covering of Graphs, and Mulder and Laskar. This is the most recent among these references. No? It is 2009. The paper deals with triangle graphs. Okay, thank you very much for listening. That's all.
Thank you very much, Dr. Herbacio. Dr. Herbacio is someone close to my heart. I don't know if we still remember that he is actually my advisor during my MS Math. So speaking of somebody close to one's heart, I'd also like to acknowledge Ziggy, who is around, the grandson of Juan Winnie, and Doc Isla, as well as Zarina, her daughter. Good afternoon to you. And at this point, yes, at this point, we'd like to ask anyone who has any question. The floor is now ready for your questions. I cannot see anything on the chat box at this point. Hello. Wala pong question? Probably later, no? So you can just send your email to Dr. Rasho, but at this point, may we request Ma'am Winnie to please put on her camera. She's on the camera for a commemorative photo with our speaker. Ma'am Winnie. May we request?
Sir.
Yes. Yes. O, sige. So, sino po ang mag-picture nito? Doc Randy, please?
Yes, tapos na po, ma'am.
Okay. Okay na po. 1, 2, smile. Thank you po. Thank you very much. Our next speaker will be introduced by Dr. Imelda S. Aniversario, a faculty of DMS. Dr. Aniversario will also be our moderator in this segment. Dr. Aniversario, the virtual floor is yours now.
Thank you, Kath. Good afternoon, everyone. And to the honorees family, good afternoon. We are honored and privileged to have our second speaker. She is actually part of our department before. She is our alumnus in the Bachelor of Science in Mathematics with a Latin honor, cum laude, in 1990. And also Master of Science in Mathematics alumnus in 1996. And a Doctor of Philosophy in Mathematics alumnus in 2019. She has been working with the Xavier University in 1995 till May 1998. And she was our colleague in the department for 14 years, no? June 1998 to 2012. But then they transferred their residence in Cagayan de Oro City. So she is connected with the University of Science and Technology of Southern Philippines since 2013 up to present. Our speaker is a previous student and an undergraduate thesis advisee of the honoree. And she has a number of research publications, especially on a strong resolving domination in the joint and corona of graphs, and strong connected metric dimension in the joint and corona of graphs, together with her advisor in PhD, Professor Dr. Helen Rara. This afternoon, she will be talking about some variants of strong metric dimension in graphs. So let's give this time to our guest speaker from USTP in CDO, Professor Dr. Peneline Lim Akal. But her talk is pre-recorded. I think someone will just play the pre-recorded talk of Penny. That's due to her common cough she was experiencing a few days. So.
Very much for allowing. Good afternoon, everyone. May hapon sa tanan. Thank you very much for allowing me to become a part of this activity, a webinar in honor of Professor Dr. Rowena T. Isla. I am one of those who enjoyed some or part of the almost 45 years of valuable service of Dr. Isla. She was my teacher in Math 17, as well as my abstract algebra courses in the undergrad. She was also my undergraduate thesis advisor, and she was also a panel member during my final oral defense for my dissertation. Ma'am Winnie is a very patient instructor. The patience even shows in the way she checks papers. She carefully notes down the errors in the proofs or in the solutions, and then points out the possible cases which were not considered in your proof or in your solution, so that by the time you receive your mark, you will not just know your score or the mark that you receive, but you will also learn and know how to go about your solutions next time. So what are the possible cases that needs to be considered, and what made your proof contain such particular error? How to correct that particular error? So she points you to the right thing to do, how to do it, especially in your solutions and in the proofs. Thank you very much, Nadine. And uh, thank you also for the time and the patience that you have shared with me, especially before I had my oral presentation. I know you were very busy then, but you really took time to sit down with me. I think that was almost 2 days, uh, checking my paper, raising questions, identifying some gaps, and then giving suggestions as to how these gaps can be um, reconciled and the paper could be improved. Um, Thank you very much, Mamreen, for being so patient, sitting down with me at the time, almost 2 days, in addition to the final oral defense. So, salamat kaayo, Mamreen, sa imong panahon, sa imong time. Again, thank you very much, Mamreen. So, moving on to my presentation, allow me to share my screen. This is the title of my dissertation, Sem Variance of the Strong Metric Dimension in Graphs. This paper was, the results generated here were under the supervision of my advisor, Dr. Helen M. Morada. The study on metric dimension was first inspired by researches in robot navigation in a network modeled by a graph. The robot determines its location in the network by landmarks or transmitters placed at sites, which may be denoted as vertices of the graph. Now here, the metric dimension is the number of transmitters required for the robot to know its position at all times in the network modeled by a graph. The metric dimension of the graph is the smallest size of a subset of vertices called a resolving set. Slater introduced the idea of the resolving set, making use of the term locating set and location number for the minimum resolving set in a graph. In 2004, Sebo introduced and Tanier introduced another variant called the metric dimension, the strong metric dimension, which is more restricted than the metric dimension. Researchers such as Sollerman or Trude, Peters, and Franzen investigated on the different approaches to the solution of the strong metric dimension problem. They have shown that the problem is equivalent to a vertex covering problem of a related graph called the resolving graph. In particular, they have shown that for any connected graph G, the strong metric dimension of G is equal to the independence number of the strong resolving graph of G. In the following slides, we will have the definitions and a few examples and comparison of the parameters. So for this definition, we have a connected graph, and we have two vertices in the graph, in the vertex set of the graph G. We call it Q and V. A vertex W strongly resolves these two vertices if V is in the shortest UVW path, UW path, or U is in the shortest VW path. The set of all these vertices satisfying this condition is what we call a strong resolving set of G. The strong metric dimension of G is denoted by S-dim of G, and this is the smallest cardinality of a strong resolving set of G. Now, if we start with a strong resolving set, and if the say S, and then the subgraph induced by this S is a non-trivial connected subgraph of G, then we get a strong connected resolving set of G. The strong connected metric dimension of G, denoted by SCR of G, is the minimum cardinality over all strong connected resolving sets of G. A strong connected resolving set of cardinality SCR of G is called an SCR set. Now, in this example for A, the blue colored vertices will give us a strong resolving set, while these two red colored vertices together with this blue one here below will give us a strong connected resolving set. Now notice that if we only consider these two red vertices, then none of the vertices B or C can strongly resolve A or B, because the shortest path from A to B, say, is this one. It will not include B. From A to C, it will also not include B, similar to a D. The shortest path from B to any of the vertices B and C will not include A. So these two alone will not give us a strong resolving set, but adding A to this group here will give us a strong connected resolving set. Now, in this case, the strong connected metric dimension is less than the strong metric dimension is less than the strong connected metric dimension of the graph G. In this other example, you see that the strong metric dimension is equal to the strong connected metric dimension of the graph H. Okay, no set smaller than the set containing two vertices, adjacent vertices, will give us a resolving set here. Okay, so next definition. This definition is very important in the results generated in the paper. So again, we have a connected graph G. A clique C in G is called a superclique. If for every pair of vertices in that set C, there exists a vertex outside of C in the vertex set of G, such that W is a neighbor of U, but it is not a neighbor of V. Or W is a neighbor of V, but it is not a neighbor of U. A superclique C is maximum in G if it is the superclique with the largest number of elements among all the supercliques in G. The superclique number, denoted by mega sub S of G, is the cardinality of a maximum superclique in G. So here in this example, we see that this group here, the group or the set containing the vertices B, C, and D, is a superclique in G. So for the vertices C and D, we can find the vertex E, which is a neighbor of C but not a neighbor of D. For the vertices D and B, A is a vertex adjacent to B but not adjacent to D. For the vertices C and D, so we can find vertices A and C, which are neighbors of one and not of the other. So in the second example, the clique identified here is not a superclique, because For the vertices V and W, the only vertex adjacent to the two outside of the set is adjacent to each of the two vertices. So it does not satisfy the condition of a superclip. So this is only a superclip. Now, for the next definition, again, we have a connected graph G. A subset S of a strong metric basis W of G is called a forcing subset of W if W is the unique strong metric basis containing S. The forcing strong resolving number F of W esteem of G of W in G is the minimum cardinality of a forcing subset for W, while the forcing strong metric dimension of G is denoted by F esteem of G. This is the smallest forcing number among all metric bases of G. The graph here has a strong metric basis consisting of the sets 1, 4, 1, 2, and 4, 3, and 3, 2. No set smaller than this can become a strong metric basis of the graph G. And notice that only these sets contain the subsets itself as a subset. So 1, 4, 1, 2, so that the forcing strong metric dimension of the graph of G is equal to 2. And in this particular example, strong metric dimension is 2, which is also equal to the strong connected metric dimension, which is 2 also, equal to the forcing strong metric dimension. For the result here, we have a non-trivial connected graph G of order n, whose dominating number or domination number of G is not equal to 1. Gamma of G is not equal to 1, and K sub 1 is equal to the singleton vertex. K1 is equal to P. Then a subset S of the vertex set of K1 plus G is a strong resolving set of K1 plus G if and only if S is equal to the vertex set of G, or S is equal to the vertex set of G less C, where C here is a superclip of G, or S is equal to the vertex set of K1 plus G less C. Another theorem is for the same result for K1 plus G, where the domination number of G is equal to 1. Now, the set S, the subset of S, is a strong resolving set of K1 plus G if and only if S is equal to the vertex set of G, or S is equal to the vertex set of G less C asterisk union the set containing the elements in the superclip C in G whose degree is equal to n minus 1. So these two results are similar, are quite similar. These two results differ in their domination number of graphs. So in this example, we have the strong resolving set ZWY here for the first graph. The superclip considered here is the set containing XY. But since Y here has degree 3, which is equal to n minus 1, our n here is equal to 4. So we add Y to the set here containing ZW. Okay, as in the previous result. We go back. So it is equal to the vertex set of G less the clique, the super clique. So the strong resolving set here is the vertex set of G less the super clique XY, but then we have a vertex whose degree is 3, that's n minus 1, so we add this vertex together with that particular set. Now in the other set here, the clique being considered is the set containing 2, 3, and 5. So from the vertex set of G, we remove the clique here, so we get the strong resolving sets of V prime plus H consisting of the vertices 1, 4. Now, for non-trivial connected graphs G and H of orders M and N respectively, a proper subset H of the vertex set of the sum of G and H is a strong resolving set of G and H, even only if at least one of the following is satisfied. Okay, so S is equal to the vertex set of the sum of G and H. We just remove the superclip in G, or we can remove the superclip in H. Or if the domination number of G and H is equal to 1, then we remove from the vertex set of G plus H the union of the superclips from G and H, and then together to this set we join the vertex in the superclip G whose degree is equal to m minus 1, m being the order of our graph G. Or you can have the other one here. To the vertex set of G plus H, we remove the union of the superclips from the graphs G and H, and then to this set we add the vertices in the superclip H whose degree is equal to n minus 1. And then we also have this result here. If the domination number of the graph G and H are both not equal to 1, then this is the strong resolving set, a proper subset of the vertex set of G plus H. So it is equal to the vertex set of G minus the superclip in G union the vertex set of H minus the superclip in H, where C sub G and C sub H are superclips in G and H respectively. Now, if G and H are non-trivial graphs, this is the strong metric dimension now, or the sum of G and H. This one, when the domination number of G and H, or G and H is equal to 1, or this when the domination number are both equal to 1. Now, we also considered a disconnected graph G with components G sub 1 up to G sub n, and H, also a disconnected graph with components H sub 1 up to H sub n. A proper subset H of the sum of V of G plus H is a strong resolving set of G plus H if and only if S satisfies either of the following. So remember here that our G is disconnected. So we have S is equal to S sub G. S sub G here is a superclip of G sub I. For some I, union the vertex set of H. Okay, and then S is equal to S sub H union the vertex set of G, where the vertex set of H minus S H is a superclick of H sub J, or sum J in set from 1 to n. Or we can have just the union of S sub G and S sub H, where the vertex set of G less S sub G and the vertex set of H less S sub H are superclicks of G sub I and H sub I for some I in this set and J in this set. So this is the result on the graph where the graph G is disconnected with components G sub I and H sub I for the graph H. Now, corollary to that result, this is now the strong metric dimension of G plus H when the graphs G and H are disconnected. So we take the sum here and take the sum of the vertices of each component and we subtract the maximum cardinality of the superclick among all the components G sub I and H sub J. Now for a connected graph G of order n greater than or equal to 2, this is the relationship between the SCR of G and SDIN of G, the strong connected metric dimension and the strong metric dimension. The maximum of the set, either SDIN of G or 2, is less than or equal to SCR of G. Of course, that's less than or equal to n. And for the strong connected resolving set of the sum, here, a proper subset S of P of G plus H is a strong connected resolving set of G plus H if and only if S is a strong resolving set of G plus H. So the results obtained in the strong metric dimension were extended to strong connected metric dimension. Okay, now for the 4C strong metric dimension, this is also the relationship here. F is dim of the graph G is less than or equal to S dim of the graph of G. Okay, and they are both greater than or equal to 1. If G is a connected graph of order n, this is n here, then F S dim of G is equal to 0 if and only if G has a unique strong metric basis. So, and then it is equal to 1 if G has at least 2 strong metric bases, one of which contains an element not in any strong metric basis of G. So this is the last result that I'm going to present, showing that the F is dim of G is equal to S dim of G. The condition when this equality is achieved. Okay, so this is equal if and only if for strong metric basis S and G, and for every X in S, we can find a vertex outside of S in the vertex set of G, such that this vertex together with S without X is a strong metric basis of G. So this ends my presentation. Thank you very much for listening.
Ma'am, you're muted, Ma'am Mills.
Okay. So we acknowledge Dr. Penelin Acal's presence, I think, to answer some questions that will be posed by the participants. Actually, we have one in the chat box from Dr. Hamil. Any practical situation or example which can be modeled or solved in terms of strong resolving sets? Usually, I think that comes from the significance or any practical situation or example which can be modeled or solved in terms of strong or just resolving sets. You had, I think, in your introduction a while ago, no?
Penny, you're still muted.
You're muted.
Yes, sorry, I unmuted. Good afternoon, everyone. It was actually mentioned in the introduction on the studies conducted by several researchers on the study. When we had the research with, when I had the research with my advisor, Dr. Rara, we actually focused on the theoretical part of the study. There were examples on applications of the strong metric dimension on the using probability. Of course, na to siya yung model. Pero wala na ako siya na, I haven't looked intently into the example. But there were studies and researches conducted already on using these concepts.
So are there some more queries about the recently paper presented? So, Pen, can you say it in a layman's term, a specific characteristic of a graph G for which the F-dim, no forcing FS-dim, but no forcing strong dimension of that graph is strictly less than the strong dimension of the graph. Is there a particular characteristic sa graph? Muted. Na-mute ka yata, Pen. Okay.
It will be strictly less than, ma'am, when the unique, when the graph contains only a unique strong metric basis. Because if that would be the case, the forcing strong metric dimension of that graph would be equal to 0. And the minimal, smallest strong metric dimension of a graph is equal to 1.
Okay, good. So I think since we have a limited time, if anyone can think of a question about the paper, you can, I think, just message our speaker. She's just one message away in our email and messenger. So again, thank you, Pen, for your time. Thank you very much, and God bless.
Okay, thank you, Dr. Aniversario and Dr. Akal. Our next speaker will now be introduced by our moderator, Dr. Sheila M. Chavez, Faculty of DMS. Dr. Sheila M. Chavez, the virtual floor is yours now.
Okay, thank you, Ma'am Cass.
Yes.
Okay, so good afternoon, everyone. So before proceeding, I would like to greet Ma'am Winnie. Happy retirement. She was my professor in my PhD algebra courses. So, kung naaalala ko, dun sa room 110 yung classes, meron dun 2 blackboard. So, every board dun hahatiin niya into 2 yung blackboard. Then, si Ma'am Isla may has a soft voice at saka maliliit lang yung handwritten sa board. So, pag start ng klase, dun siya sa right, sa first blackboard, dito sa left. So, at the end ng class, so nandun na siya sa dulo. So, na-observe ko lang, ma'am, seldom ka lang mag-erase ng board. Parang towards, after na ng class talaga. Or kung mag-erase ng few times lang. Okay. Yun po yung naaalala ko sa'yo. Okay. So, now, let's go to our next presenter. So, it's an honor to introduce to you a friend and one of my classmates who was a PhD math student of the Department of Mathematics and Statistics from 2010 to 2014. He actually went through some bridging courses because his undergraduate degree is BS in secondary education, major in mathematics. Even though he had a MS Math degree from Bohol State University. I have witnessed some of his struggles during the first few years in the program, but because he had the determination and dedication to finish the program, he obtained his PhD math degree on time. Our speaker was actually the first PhD math advisee of Professor Rowena Isla. In fact, together with Professor Sergio Cano Jr., as mentioned by Ma'am Cassie a while ago, they have published 3 articles related to his dissertation topic. So after graduation here in IIT, he went back to his sending institution, the Bohol State University in Balilihan campus, and now with a faculty rank of an associate professor from the College of Technology and Allied Sciences. Also, he is the director of Quality Management System of Bohol State University, Balilihan campus, and serves as a faculty for the MS Math program of BSU main campus in Tagbilaran City. With his research background, he is now mentoring few of their math graduate students. Ladies, he is married, a father of 3, and a certified YouTuber. Ladies and gentlemen, please help me welcome by watching first the video presentation of Dr. Emiliano C. Maravilla. Jan, please. Thank you.
Good day, everyone. I will be presenting the concept on fair total domination in graphs. Let me first define 3 parameters that comprises understanding. So first, we're going to have the definition of dominating set. So a set S subset of V of J is a dominating set of J if for every V outside S, there exists U and S such that UV is an edge set of J. That is, the close neighborhood of S in J is equal to V of J. We have the domination numbers denoted by gamma of J, which is the smallest cardinality of a dominating set of J. Next is we have an example. A graph G with domination number is equal to 2. Next is the definition of a fair dominating set. So let G be a connected graph. A fair dominating set denoted by FD set in G is a KFD set for some integer k greater than or equal to 1. Thus, a dominating set S subset of G is an FD set in G if for every two distinct vertices U and V outside S, the cardinality of the intersection of the neighborhood of U and S is equal to the cardinality of the intersection of the neighborhood of V and S. Fair domination number of G is denoted by gamma FD of G. A fair dominating set of the cardinality gamma FD of G is called the minimum fair dominating set or a gamma FD set of G. So we have here an example. We say a graph G with a gamma FD of G is equal to 5. So let us try to check. Okay, so we have here, we choose V2, V3, V6, and V7, and V9. Notice that all vertices outside S is connected to one vertex in S respectively. So we have gamma 1 FD of J is equal to 5. Let's try another possibility. We have here V1, V4, V5, V6, V7, and V8. Note that the vertices outside S is connected to exactly two vertices in S. So therefore, we have the gamma 2 FD of G is equal to 6. So we have here the definition of fair total dominating set or FTD set. A set S of a connected graph of G is a total dominating set S of G such that for every two distinct vertices U and V outside S, the cardinality of the intersection of the neighborhood of U is equal to the cardinality of the intersection of the neighborhood of V and S. That is, S is both fair and total dominating set of J. So we have here the notation gamma FTD of J is the minimum cardinality of an FTD set, and a fair total dominating set of cardinality gamma FTD of J is called the minimum fair total dominating set or the gamma FTD set of J. So we have here an example, a graph J which has a total dominating set but not fair. Not fair because the vertices outside S, V1 has two neighbors from S while V2 has only one neighbor from S. So it is not fair total. We have graph J with gamma 1 FTD of J is equal to 2. So we have all vertices outside S has exactly one neighbor from S. And we have V3 and V4 are adjacent. A graph J with gamma 2 FTD of G is equal to 3. All vertices outside S is adjacent to exactly two vertices in S. So we have here some results of our study. We have the first one, the fair total domination in the join of graphs. So we have here two connected graphs, and S subset in the join is an FTD set of the join if and only if one of the following statement holds. First, S subset of V of J and S is a cardinality S FTD set of G. Likewise, when S is a subset of V of H. S is equal to V of G union with S sub H, where S sub H is an RFD set of H for some positive integer R. Similarly, with condition D. And we have condition A, S is equal to the union of S sub J and S sub H, where S sub J is a KFD set of J and S sub H is an RFD set of H for some positive integers K and R such that K plus the cardinality of S sub H is equal to R plus the cardinality of S sub G. So we have here the gamma FTD of the join. It is equal to the minimum of the Q prime G, Q prime H, and Q prime B where it is defined below. Next one is the pair total domination in the corona of graphs. So we have G is a connected graph and H be any graph. Then C is an FTD set in the corona if and only if one of the following holds. So we have the pair C is equal to the vertex set of G. We have condition 2, C is equal to the union of S sub V, where V is in V of G, where each S sub V is a KFTD set of the copies of H, and the cardinality of S sub V is exactly K. Third, C is equal to V of G union with the union of S sub B, where V is in V of G, where either the S sub B is equal to the vertex set of the copies of H for each V in V of G, or each S sub V is a K minus 1 FD set for some K greater than 1. Then the fourth condition, C is equal to A union with the union of the vertex set of the copies of H, where V is in V of G, where A is an RFD set and C is a KFD set, and the cardinality of the vertex set of H is equal to K minus R greater than 0. So we have here the gamma FTD in the corona is equal to the cardinality of V of G. So we have here the fair total domination, the composition of graphs. We have G and H are non-trivial connected graphs if C is defined in this manner, is an FTD set in the composition, then T sub X is an FD set for each X, E in S, and either S is a total dominating set in G or S is a dominating set in G, and T sub X is an FTD set of H for each X in S outside the neighborhood of S in G. The next result, C is an FTD set in the composition if the conditions above are satisfied. We have here the last result. We have G and H being non-trivial connected graphs. Then the gamma FTD in the composition is less than or equal to the gamma FD of G times the cardinality of the vertex set of H. Moreover, if G is regular, then the gamma FTD in the composition is less than or equal to the minimum of the gamma FD of G times the cardinality of the vertex set of H, and gamma FD of H times the cardinality of the vertex set of G. The following are the references of my study. Thank you very much for listening. Before I will end this video, let me grab the opportunity to thank, magpasalamat ko kayo sa MSU-IIT nga gidawat gyud mi ninyo. Gidawat mi ninyo as a student nga kahibaw man gyud mi nga at first palang daan pag screen sa among TOR is mura man ka sakto ba ni ato ang move nga ni eskwela taog PhD mathematics. I'm very thankful nga despite sa mga difficulties nga among agian, instructors of MSU-IIT ning tabang yun namo, ning encourage namo. Karon sige pa ko recall, giunsa man ako to pag-survive, giunsa na mo pag-survive. There was a time na nanghid mi ni Dr. Hamil kung naka numdum pa si Sir Hamil, sir mo back out tabi sir. Na Dr. Hamil was very positive. O ano mo back out man mo nga o kani inyong INC usara may solusyon ani inyo ra man intikan og exam. So ingana ka encouraging ang mga faculty sa MSU-IIT, and very thankful kayo mi nga wala mi pasagday gipahilo na mi tarong from the beginning sa among journey sa IIT, from bridging up to dissertation gipahilo na gid mi taman. Hi Ma'am Isla. Hello Ma'am. Ikaw milak. Hi Ma'am. So Graduate niyo 2014. Pag-chat pa lang ni Ma'am ni Dr. Rara nga mo present ko, wala ko kulba ma'am, pero na-excite ko nga mo present kay mao na ni time nga gusto ko express ako ang gratitude kay kani si Ma'am Isla is very motherly gid kay ni si Ma'am. So kada adto na ko sa faculty is kan bang pinahiluna yun. Si Ma'am is very soft spoken po. Kamantay siya ni si Ma'am nako nga ako di man gid ko outspoken nga pagkatao, maghilom-hilom na gid ko. So si Ma'am is email nakasabot pa ka email na apoy time nga tungod sa akong kakulba bali or ikulbaan ko or maikog ko usahay kay na time nga marag yes ma'am nga na so makamantay siya ni si Ma'am Isla mura out of concentration ako. Ma'am, I am blessed na ikaw akong nahimong advisor. I hope ma'am nga during time nga imo kong mentoran, I hope nga nakita din mo nga ko ang struggle or paningkamot. Ma'am, congratulations man for mao ni nga time nga you can have your free time, and God bless you always ma'am. Ug once again salamat kay ma'am sa imuhang pag-accommodate nako as your advisee. Sa tanang mga instructors nako sa MSU-IIT, may instructor man o dili instructor, nabati gud namo nga kami taga Bohol is very welcome diha. Very welcome sa department, although at first nag-adjust yun migtaman, nag-adjust migtaman tungod sa environment sa amo ang subject, but nakapot na may tungod nahuman may tungod sa tabang sa mga faculty sa MSU. Amo gining bawnon ma'am og share sa amo ang among degree. Every time makita gid ko nga doktor na ko, ang primary gud ako mahamduman ang MSU-IIT. All your encouragement, dako ka itong tabang namo nga mo graduate may sa MSU-IIT. Ma'am Isla, salamat kay ma'am. God bless you. Good day everyone. I will be presenting the concept on.
Okay.
Thank you. Yes, go ahead, Dr. Chavez.
Emil, are you here? Medyo mahina daw kasi yung net niya, ma'am. I don't know kung nakapasok siya. Emil, are you here? I think none, So, I think let's just proceed, Ma'am Ka.
Okay, thank you. Okay, Ma'am Sheila, thank you. Dr. Chavez, thank you, Dr. Maravilla, for that very heartwarming message. We are touched by that one. I'm sure our honor is touched too. At this point, we will now have our fourth and final speaker, who will be introduced by our next moderator, Dr. Melmar A. Labendia, a faculty of DMS. Sir, the virtual floor is now yours.
Good afternoon. Can you hear me?
Yes, sir.
Okay. Before I introduce the last speaker, I would like to bid Ma'am Winnie. Happy retirement, Ma'am.
Thank you.
Our last plenary speaker is a professor in the Department of Math and Stat of MSU-IIT. He finished his PhD, Doctor of Philosophy in Mathematics from the University of the Philippines, Diliman, with dissertation research in the field of integration theory at the National University of Singapore. Our speaker is a prolific researcher in pure mathematics, and I know that my colleagues can affirm, and has produced over 100, I cannot say how many, but over 100 publications in various academic peer-reviewed international journals. And he has several papers in graph theory on domination in graphs, integration theory in hen-stack integration, topology on variations of open sets in topological spaces, and recently on algebraic hyperstructures. Our speaker is not only a prolific researcher in pure mathematics, but also a passionate mathematics educator, as we all know. He's also a graduate of PhD Mathematical Sciences, Mathematics Education. And he has mentored and helped several students in PhD Mathematics and Mathematics Education who are faculties from different universities, mostly in Visayas and Mindanao. And I know some of the students from Bohol could also testify. And because of his generosity, he has also mentored and encouraged most of our colleagues from the Department of Mathematics and Statistics of MSU-IIT. And I'm one of the recipients of those. And our speaker was also one of the pioneers of MSP, 10, 12 in BARM, before it was 10, 12 in ARM, which is an active organization that promotes mathematics research and education not only in regions 10, 12 in BARM, but also in Mindanao. He has been invited in different conferences in the country and has received numerous academic awards which include the Outstanding Young Scientist of the Philippines. Actually, di ko mahuman kung daghan pa kong istorya kay daghan yung kani sa achievement. So please welcome our last plenary speaker who will talk about from domination to half domination, Professor Dr. Sergio Arcanoy Jr.
Good afternoon. Thank you for that kind introduction. Okay, I would like to dedicate this presentation to Professor Winnie Isla, one of my chat mates at room 116. So the topic is from domination to half domination. Domination in a graph has been one of the most widely studied concepts in graph theory. In fact, a lot of people in Mindanao and in the Visayas are into domination and some of its parameters. The concept of domination was formally studied by Burge in 1958, although 100 years prior to that year, there had been some references already concerning domination related concepts and parameters. In 2015, these two Indian mathematicians defined and studied the concept of half domination. These two concepts and some of their variations actually find applications in various types of networks. In particular, they are utilized in facility location and in designing protection strategies. These are the concepts one needs to formally define a dominating set on a graph. Have the open neighborhood of vertex, which of course consists of vertices adjacent to it. And then we have the closed neighborhood, which is obtained by just adjoining the vertex to its open neighborhood. And then for any subset A, we define the open neighborhood as the union of the open neighborhoods of the vertices in that set. And if we adjoin that set A to its open neighborhood, we get the closed neighborhood of the set. And a subset S is a dominating set in that graph if the closed neighborhood of that set coincides the vertex set of graph G. In other words, set S is a dominating set if it's outside the set is adjacent to some vertex in that set. And we are interested in the minimum size of a dominating set of a graph. And the minimum size of a dominating set is referred to as the domination number of graph G. And then from we can actually hop a bit to get the definition, corresponding definition of a half dominating set. So instead of unit distance, we can use 2. So we also defined the open half neighborhood of a vertex as the set of all vertices that are at a distance 2, exactly 2 from that vertex. And then we have a closed neighborhood of a vertex, open half neighborhood of a subset. As you can see, it's just the union open half neighborhoods of the vertices in that set. Then we have the closed half neighborhood that by just adjoining the set in its open or open half neighborhood. Then a subset F is a half dominating if the closed half neighborhood of that set is equal to the vertex set. And again, we are interested in the minimum size of a half dominating set, a graph G, and that size of a half dominating set is called the half domination number of G. Given a graph, the difference of the domination and, or if we consider the difference of the domination and half domination number of graph, 3 possibilities may happen. Okay, the first one is that the difference is 0. It can be positive, and of course, the difference can be negative. Okay, this is just a simple illustration. Okay, consider this graph, and then consider the vertices B and C. Okay, F and G, F, G, and A are actually half dominated by vertex B, while vertices D and E are half dominated by C. And the set consisting of these is a minimum half dominating of that. The half domination number of this graph G is equal to 2. But this graph cannot be dominated by 2 vertices. Okay, if we the vertex A together with vertices B and C, we find that these vertices actually constitute minimum domain of graph G. Actually, A can be replaced by D or E, and therefore the domination number of this graph G is equal to 3. This result we obtained together, or I together with an advisee, sort of a realization result Okay, for each integer n at least one, there exists a connected graph G such that this difference is equal to n. And for each integer n greater than or equal to one can also construct a connected graph G such that this difference is equal to. The proof is easy because this is also an easy result. So for I, we consider the complete graph of or complete graph of order n plus. Of course, the domination number of a complete graph is equal, but the half domination of a complete graph is equal to its order. So it will be n plus 1 minus 1, and that will give us for the first part. And for the second part, we simply consider the graph G obtained from K1 n plus 2 by adding the edges V sub I, W sub J, I from 1 to n plus. I'm sorry, by adding the edges V sub I, W sub I, I from 1 up to n plus 1. If we consider the vertices V sub 0 and V sub 1, we also see that these two vertices half dominate the other vertices. Okay, W sub i's, for example, are half dominated by V sub 0, and the rest of the V sub i's are half dominated by V sub 1. As you can see, the distance between V sub 2 and V sub 1 is equal to. So V sub 2 up to V sub n are actually half dominated V sub 1. So the half domination number of this graph is equal to 2. Okay, but the dominant number is exactly equal to n plus 2. Okay, so the set consisting of the V sub i's is a minimum set of this graph. This is a more general realization result. Okay, if we have two positive integers, this part A is between 2 and B, one can construct a connected graph G such that the half domination and the domination is B. And for the second part, if A is at least 3, at most equal to B, one can find or construct a graph H such that the domination of that graph is A and the half domination is B. Okay, so this is the proof that is for the first part. And this set listing of vertices X sub I is a minimum half dominating set. So the half domination and the domination number of or numbers of this graph coincide. Okay, for the case A is strictly less than B, the difference, we just consider this graph G. And for the second part, we consider this graph G. Okay. To define a variant of half domination, we call this one a global half domination. Subset S is a global half domination of graph G if it is a half dominating set of its complement G bar. And the smallest size of a dominating set of G denoted by gamma sub G is called the global half domination number of G. Okay, so consider the graph G, C and D half dominate the other vertices. So the half domination of G is 2. If you look at the uh, the vertices C and D also half dominate the other vertices. So this is an illustration which has a global half domination equal to 2. As a simple remark, for any graph G, the half domination is at most equal to the global half domination, and the global half domination is the same as the global half domination of its complement, and the domination is in between 1 and the order of the graph. And in particular, we get the lower one if and only if G is the trivial graph. So for non-trivial graphs, gamma or the global half domination uh, 2. And then this is a result, a characterization of graphs which for whose global half domination is the same as its order. So the global half domination is equal to the order of the graph if and only if every component of G or G bar is complete. Moreover, these two are true. The complement of the open neighborhood of V is an independent set. And for each A in for each non-neighbor of V, V and A have the same open neighborhoods. And as a direct consequence, the global half domination of the graph and the star graph K1n minus 1 is equal to the order of the graphs. This is for all n greater than or equal to 2. And we have this realization result involving the half domination and the global half domination of a graph. Okay, we have two A and D satisfying that property or condition that is between 2 and A is at most equal to B. Then one can construct a connected graph that the half domination is A and the global half domination is equal to B. So that is the proof. And as a corollary, the difference of these two parameters can actually be made arbitrarily. We consider a complementary for a graph G, the complementary prism G bar is actually the graph formed by or formed from the union, this joint union of G and its complement. And then after you add the edge V bar for every B in V of G. So as as illustrations, we consider the complementary prism K3 bar. As you can see, I'm using the initials Rowena T and I bar, for the corresponding vertical. Okay. And Haynes and actually obtained this result that the domination number of the complementary prism is between the maximum of number of G and the domination number of its complement, and an upper bound, the sum of the domination number. And we have this result for any connected graph of order n. If G is a non-trivial graph with domination number equal to G, then the domination number of the prism, complementary prism, is 1 plus the domination number of minus V bar, where V here is a dominating vertex. We can talk of vertex because the domination number of G is equal to the vertex that dominates every other vertices of graph G. And the domination of Kn equal to n as a particular case. If n is greater than or equal to 1, then the half domination of the complementary is equal to 2. In particular, B bounding vertex V bar is gamma H set of bar, meaning this is a minimum half dominating set. And this is true for every vertex in graph G. And for at least equal to 2, the global half domination complementary prism is at most equal to the minimum of the order of G and twice the global half domination of graph G. And then for the complete multipart type graph, satisfies conditions, we have this domination number of the complementary prism, and complementary prism. And then as a lemma, if G is a graph with domination number equal to 1, and if S is a global half dominating set of G of the complementary prism, then B is in S, or the corresponding vertex V bar is in S, ever B is a dominating vertex of graph G. Okay, and then we obtain the global half domination of multipartite graph satisfying the above conditions. Also consider a shadow graph. The shadow graph S of G of a graph by taking two copies of G, say 1 and G sub 2, and joining each vertex U of G1 to the neighbors of the corresponding vertex U prime of G2. So as an illustration, we consider the shadow graph SP5. So below is G sub 1. G sub 1 is, of course, P sub 5. G sub 2 is just a copy of G, or P5, so it's also P5. Then, for example, A is adjacent to B, therefore, by definition, A will be adjacent to B prime, and then so on and so forth to obtain. And then lemma or result. I'm sorry, this D to G should be S of G. Okay, G is a non-trivial connected graph. G1 and G2 are of G, the definition of the shadow graph. Okay, if W is in W prime is in G2, this W prime is of course the vertex corresponding to W, then the closed half neighborhood W in the shadow graph is equal to the union close neighborhoods of W in G1 and W prime in G2. And is also equal to the closed half neighborhood of in the shadow graph. Of course, that's easy to prove. It's an illustration. One can consider the vertex C. Okay, in G1, half neighbors of C are A and E. So if we consider the closed half neighborhoods, it will include C. The closed half neighborhood of C prime, of course, is the set consisting of A prime, C prime, and E prime. And C is the closed half neighborhood C in the shadow graph. So, for example, A prime is at a distance 2 from C. So this is a half neighbor of C, also C prime and E prime. Okay, and similarly, that union is the closed half neighborhood or a closed half neighborhood of C prime. So, yeah. The shadow graph is never a complete graph for non-trivial graphs, and it's connected if and only if G is connected. And every of the shadow graph is a complete graph if and only if G is the empty. And every component of the complement shadow graph is a complete graph if and only if G is the complete graph or G is a complete multipartite graph. We have this result, which gives us the half domination number of the shadow graph. So for connected graphs, the half domination number of the shadow graph is just the same as the half domination number of graph G. If G is a graph with R isolated and K non-trivial components, 2 times R, twice the number of components. And we have this bound for the global half domination of the shadow graph. It's bounded by twice the global half of graph G. And this result actually says that this bound twice the global half domination is a tight bound. Okay, we get 2n for the global half domination of the shadow graph if and only the empty graph or G is complete multipartite graph. Well, just 2 days or a day ago, I looked at Google Scholar and I looked at the publications of our retiree, and I was able to construct this graph, okay, actually showing the retirees number 1. So this is actually a graph showing Winnie's number 1. So I do not have to mention names of those representing these vertices. Of course, W here refers to Winnie or Dr. Isla. And 2 vertices, which of vertex is of course an individual, a name of a person, and an advisee or a co-researcher. of the retiree. Two vertices are adjacent if and only if they have a joint paper, a joint published paper. And as you can see, that vertex W. So our retiree dominates every in this graph. I call this one the RTI graph. And therefore, the domination number of RTI is equal to 1. Okay, that vertex does not half dominate any of the vertices, the other vertices. So we need another vertex. And these two vertices now half dominate the other vertices. And therefore, the half domination number of the graph is equal to 2. Okay. And for global half domination, we need to look at the graph. Okay, the complement of this graph will consist two components. The first one will just be the isolated vertex, the trivial component, no? W, that will be, because it's adjacent to every vertex. So in the complement, that will constitute a trivial component, and the other components will be induced by other vertices. Now, four vertices are actually dominating vertices, and therefore be included in any half dominating or global half dominating of the set. But none of these four can half dominate the other 5 vertices. And for the other 5 vertices here, this can actually be half dominated by 2, at least 2 vertices, specifically these 2 vertices. And the global half dominating, the global half domination number of this graph, the RTI graph, is equal to 7. So we have this. And surprisingly, the sum of these 3 quantities is equal to 10, and that corresponds to that sum of cardinalities. Okay, thank you. And these are some of the future problems that, not future, but future problems one can consider. So I'm wishing you win an enjoyable retirement. May you have all the best this retirement brings. The math surely needs you. God bless. Thank you.
Okay.
Dr. Labandia?
Yeah.
Yes, thank you.
Thank you, Dr. Canoy, for that very substantial and inspiring message. Talk. So now let's welcome questions about the topic presented by Dr. Canoy. Okay. I have a question, Dr. Canoy. When you mentioned about for any graph something, and you have a result about half domination number, you're assuming there that the graph has at least 1/2 degree. Otherwise, you cannot find a half dominating set like the complete graph or the C3, right?
What do you mean?
I mean, if the graph is complete, I don't think if we can find a half domination.
Yeah. As I've mentioned, the half domination number of any complete graph is equal to the order.
Oh yeah. Okay. It's equal to the order.
Yeah. you have the whole vertex set as the half as minimum half dominating set.
Okay.
Yeah. But the domination number is just equal to 1.
Okay. Any question? So I think none. Thank you very much.
You're welcome.
Okay, thank you, Dr. Lavendia. Thank you, Dr. Canoy. May we now request all the speakers, Dr. Akal, Dr. Maravilla, Dr. Hervasio, Dr. Canoy, for a commemorative photo with our honoree. So will you please open your cameras, and we request somebody to give a cue for the photo op, please. So I can see Dr. Canoy and Mom Winnie, Dr. Akal, is she still with us? And Dr. Maravilla. Sir Randy, are you taking the pictures now?
Yes, ma'am. I'm taking.
Okay, thank you. Okay, thank you once again. Now let us give a virtual applause for all our speakers. And may we request all the participants to please open your cameras for our photo opportunity. So all participants, please put on your camera so that we can have a photo op with our honoree. Sir Rands, medyo marami tayo. Kanina over 100 tayo. You're now 93.
Okay, I'm taking pictures now.
Okay, taking pictures now. Smile, everyone. Please let us know, sir, pag tapos na po.
Yes, I'm done, ma'am.
Okay, thank you very much. If you would like to receive a certificate of participation, please fill up the evaluation sheet. I guess, Sir John, did you put it in our chat box already, the link? And then your certificate will be sent to you later via email. Thank you very much. Now, you might have wondered why the web conference is called Graphs and Memories. So to kick off the second part of this tribute, allow me to show you a video presentation entitled Memories.
Thank you for the love.
And now for the second part of this tribute, let me now turn over the virtual floor to Dr. Gina A. Malacas.